Hello, and welcome to this AMETEK Land webinar. Now let me introduce today's presenter. With us today, we have Manfred Hayek from AMETEK Land. To read more about our presenter today, please look at the speaker bio window right next to the main presentation window. And with that, I'd like to pass things along to Manfred to get this webinar started. So go right ahead.
Welcome to the E360 webinar for non-contact temperature measurement for heavy industry process control in the Industry 4.0 environment. Please let me shortly introduce myself. My name is Manfred Hayek, and I'm the Global Manager for infrared products like parameter thermal images and scanners used for advanced non-contact temperature measurement and controlling. While I worked in the field of infrared metrology since more than 25 years, and mainly in the field of non-contact temperature measurement, I'm with AMETEK Land since 2016. This is the main content I will go through during this webinar. Traditional measurement equipment and interfacing, transfer to digital technologies and interfacing, digital communication and Industry 4.0, smart functionalities in measurement equipment, autonomous and software-based system designs, image pro monitoring, analysis and process control, questions and answers, and finally, how to contact us. What are the main takeaways of this webinar? Understand the differences between analog and new smart and digital industrial non-contact temperature measurement technologies. Learn about the new smart and intelligent functionalities and interfaces of these technologies. Find out about the opportunities and benefits of existing and future interfacing and data communications. Discover the benefits and applications of the new AMETEK Land thermal imaging range. Okay, let's start with a short overview of traditional measurement equipment and interfacing. Still, a certain amount of traditional measurement equipment is available in heavy industry applications like analog parameters, scanners, or thermal images. These devices work reliable for tens of years while processing and outputting the measurement data, the temperature, still via analog outputs like 0 or 4 to 20 milliamperes or 0 to 10 volts. Internal signal processing functionalities, an external emissivity value or reset signal for time functions were initiated, for example, through 4 to 20 milliampere instrument inputs or integrated IOs. Additional digital signal processors were used to convert the analog measurement signal into a digital one for further processing and providing the data to analog and digital interfaces like RS-485. Analog measurement devices and systems more and more get obsolete and are replaced by fully digital ones, including digital communication interfacing and features. These are typical installations of such analog traditional measurement equipment, starting with a typical analog instrument or parameter, outputting the temperature value via linear 4 to 20 milliampere output, and receiving the 4 to 20 milliampere input, for example, to receive and set the emissivity which was chosen on the analog controller installed in the switch cabinet. The second installation, for example, is with 4 analog parameters connected to a digital controller. The controller receives the measurement data from these heads and also sends a 4 to 20 milliampere signal to the parameters, for example, to set the emissivity. The controller itself was able to process this data, to do some time functions, peak pickings, limit switches, or anything else, and outputs the measurement data and processed data via analog IOs or digital IOs. The third example is with an infrared line scanner connected to a line scan controller, which completely controls the system, and you could set up the scanner with this controller, and finally outputting the data with an additional I/O module. Last but not least, a thermal imaging installation where was a direct interface, bidirectional, between the thermal imager and a controller unit, while this controller unit was connected to an I/O module and provides a digital interface to any additional software. Let's discuss about the transfer to digital technologies and interfacing. With bigger and faster data communications, digital interfacing in bus systems, measurement data from temperature sensors like parameters, scanners, or thermal images are presented to bigger process and plant data. Based on industrial Ethernet networks, protocols like Modbus or Profinet, and open platform communications, unified architectures, are more and more common in the industry. For example, IO-Link is a standardized I/O technology for communication with sensors and actuators. A point-to-point communication is based on a 3-wire connection. Amatate-Glen parameters and processes can easily be integrated into existing IO-Link networks. Due to high and fast data flow of thermal images and scanners, typically gigabit Ethernet interfaces and various protocols are used and can be easily converted by protocol converters to different protocol types. These are some examples for actual non-contact temperature measurement sensors and systems. Starting with the spot parameter, providing analog IOs, 0 or 4 to 20 milliamperes, providing CMD relay outs, digital IOs, and providing digital interfacing via Power over Ethernet connection, TCP/IP Modbus TCP. The LSB HD scanner, which is an infrared line scanner, provides a one-cable digital interface via Power over Ethernet industrial Ethernet connection. And last but not least, the new LWIR 640 thermal imager provides analog IOs, 0 or 4 to 20 milliampere, CMD relay outs, digital IOs, and the digital interface, which is also a Power over Ethernet interface. With this slide, I would like to introduce a typical network data configuration for a thermal imager, scanner, or parameter, or even more devices in one network. They all provide industrial Ethernet interfacing and additional analog interfacing. They are powered by Power over Ethernet, connected to one network. If more devices are connected, they're typically connected via an Ethernet switch, then connected to a main server for data processing, analyzing, monitoring, and of course, connected to the plant network for process control, for data storage, cloud data, or any clients for remote access. Let's talk about digital communication and Industry 4.0. What does Industry 4.0 mean? It describes the digitalization of industrial processes and the associated bidirectional data exchange via digital interfaces, enabling comprehensive and automated communication between machines, sensors, and operators. Based on these bidirectional industrial Ethernet interfacing, multiple protocols are available, such as Modbus TCP or Profinet, to easily integrate temperature sensors into existing or new plant and data networks. Remote access allows maintenance and service from any point in or outside the plant, and also monitoring the process from remote. Higher level databases combine the data from many of all active sensors for long-term data storage, trending, process monitoring, and extended analysis and control. These networks are easy to extend or replace of sensors in the plant and data network. With the ongoing digitalization of sensors and systems, smart functionalities are introduced into these measurement equipments and further developed. Let's discuss in detail. With the next slides, I would like to go through the smart functions of the spot application parameter and the new LWIR 640 thermal imager in some more detail. For example, in aluminium production processes or steel strip annealing or galvanizing lines, the conditions of the material or the surface to be measured can change massively during the measurement. In such non-contact temperature measurement applications, where usual instruments do not work sufficiently, additional intelligent, so-called smart functionalities are available. Spot application parameters provide several smart measurement algorithms to automatically adjust to the actual process and material and surface conditions, resulting into reliable and high accurate temperature readings for process control. In hot furnace environments, for example, it is necessary to compensate for the hotter background of the furnace refractory, which is reflected on the surface on the material to be measured, which is done by an instrument integrated background compensation algorithm. Standard mono or ratio parameters are typically used in applications where the application conditions or the surface conditions, the surface emissivity, does not change very much. In applications like discussed before, in aluminium applications, where there may be different oxide layer on the aluminium surface resulting into different and changing emissivities, or in steel strip coating lines, annealing or galvanizing lines, where the conditions and the surface emissivity is not only changing, but also is very low, application parameters are needed to compensate for. These application parameters, like the spot AL for aluminium applications, or the spot GS for coating or galvannealing applications, automatically determines the correct emissivity or non-grayness of the measured object in the process by an algorithm and corrects the temperature reading online. You just need to choose an algorithm for this process. All these spot parameters include an integrated web server, which can be used in addition to analog or even the digital connection to the plant control system. With this web server, you can not only monitor the actual functionalities, but you also can configure the whole system, control the whole system by just using a standard browser via the existing network connection. Introducing the new smart LWIR 640 thermal imager from AMETEK Land. These smart functionalities and multiple interfaces enable this imager to be easily integrated into new and existing processes and furnace controls. Thermal imaging cameras and systems play an important role in modern industrial processing and furnace applications, meeting the increasing demands on product quality, process efficiency, energy saving, predictive maintenance, and emission reduction. With the integrated web server and multiple I/O options, the camera is able to be used autonomously. The web server provides an easy camera access, control, and setup just using a standard browser like the spot parameter I introduced the slide before. In addition, the Image Pro advanced image and processing software for controlling, monitoring, analyzing, and capturing data cover the requirements of actual and future process imaging demands in the Industry 4.0 environment. Let me go through some smart functionalities of the new LWIR thermal imager. As already discussed, it contains a web server which can be easily accessed by just using a standard browser in the same network. Via the Power over Ethernet interface and the onboard and configurable I/Os, the camera can be completely used autonomous, with no need for additional software or extra I/O modules. The integrated web server gives a full control over the onboard I/O configuration, functionalities, and enables a full live view. Integrated region of interests and these measurement value analysis and time functions enable a value processing for processing, control, and monitoring. This is a typical configuration using the thermal imager, the LWIR640 autonomous. So it is connected by the Power over Ethernet connection. So you can use the integrated web server and configure the whole camera and the I/Os. And you can then use the analog out, the analog in, the relay out, or digital in, and configure all these functionalities. By using the web server, you have several options to going in more detail, defining all these three IOEs, defining the I/Os, setting alarms, setting threshold limits, whatever you want to make the camera very, very variable for many, many different applications. If you need to install more than one or even 10 or 15 thermal images in one place, for example, you have a critical vessel monitoring system or a process where several process locations need to be monitored and measured, you can connect more images via the gigabit Ethernet to the same network using an Ethernet switch. Connect this data to a workstation server, which is then connected to the plant network, data storage, cloud data, clients, process controls. All is possible. With these smart sensors and functionalities, Industry 4.0, Internet of Things, cloud data, all the data and pre-processed measuring data can be used in the whole plant and process network to control the process, to store and to analyze actual and historical data, to upload data to data clouds, and to integrate more than just thermal temperature sensors together with a main software and Ethernet connection. It is a whole plant measurement network. While smart sensors like parameters or thermal images can be used autonomous, Typically, in bigger multi-sensor applications, the advanced ImagePro thermal imaging, monitoring, analysis, and control software is a key part of such process and measurement system. ImagePro provides extensive functionalities and further process control capabilities and can handle up to 16 images per installation. Specified application versions like the ImagePro SDS for automatic slack detection and liquid metal tapping streams, or the ImagePro AM asset monitor for continuous temperature monitoring and trending detection of critical vessel and furnace applications are available too. The whole sensor or camera access and configuration can be done via the ImagePro software too, in addition to the integrated autonomous functionalities of the LWIR640 thermal imager. With this, I would like to finish the part of the webinar and go over to the questions and answers part. We already received several questions I would like to go through during this webinar, while you can contact us directly for further questions. The first question: will analog and digital interfaces both still be available in new non-contact temperature measurement equipment? Yes, of course. Traditional analog inputs and outputs will still be available with this equipment. The interface options will be extended by digital interfaces. For example, the spot parameter provides an industrial power over Ethernet interface, while additional analog inputs and outputs are available on a separate connection. What is the smart measurement technology included in the latest parameter scanners and thermal imagers? To answer this question, I would like to use a citation from Times Sunday Times. The idea behind smart technology is that your appliances do the thinking for you. Meaning smart technologies is a combination of networked sensors and technologies, data consolidation and analysis. While sensors become intelligent, communicate with each other at the field level and pre-process measurement data automatically being available online at the control level. This obviously is a practical question. How should we approach replacing existing analog equipment with new digital measurement equipment systems? As already mentioned before, the traditional analog interfaces will still be available on the instrument side and on the control side, for example, 4 or 0 to 20 milliampere IOs, relay, and digital IOs. New instruments can be connected to the same analog connections and IOs the old instruments were connected to before, including the same and more functionalities. In addition, the whole digital interfaces can be used for network integration, data storage, and many more. These work fully bidirectional and with internal web servers provided, they can be accessed via the integrated digital interface too. Does autonomous operation mean, and can you give some application examples? Is additional software needed for the smart temperature measurement equipment, and what is available? Okay, these are more than one questions. The basic autonomous operation is the ability to operate as a standalone sensor, a parameter, scanner or camera, without the need of any additional software or further equipment except power supplies, connections, and mechanical accessories. With this example, I would like to answer the other questions. For example, in flare stack monitoring applications, typically thermal imagers are installed in the field, far away from any operator room. These kind of installations are fully autonomous, meaning the thermal imagers and the measurement and detection parameters are configured using the onboard web server. With this, the integrated IOs provide temperature output, pre- and full alarms, and many more. An additional software is an optional feature, for example, for combining more than one images and monitoring the results. Next question. How do you integrate many measurement devices, such as thermal imagers, into one system? Can you give an example? Well, this of course is a main question regarding a real sensor network configuration. Industrial Ethernet is a key hardware interface commonly used throughout the industry. Different Ethernet protocols such as Modbus TCP, Profibus, OPC-US, etc. can be used for bidirectional data communication between several sensors and the plant and control network. By configuration of different sensor IP addresses, they can easily integrate it into existing or new measurement or plant networks by just using an Ethernet switch. The last question I would like to answer during this webinar is a look into the future. So what is the future of the integration of measurement devices into data clouds and Internet of Things environments? Well, the main precondition is the digital communication and interfacing of the instruments. Let us look into the future. With the ongoing development of digital technologies, data clouding, and Internet of Things, fast and fully digital communication based on smart data processing, more and more sensors will be integrated into plant control and data networks on field and control levels. Big data clouds enable the data merging and processing, resulting into deeper process control and understanding, and foresight acting based on the results of intelligent linking and data processing. I'm sure you will have further questions. Please feel free to contact us directly and send your questions to us, while a specialist will come back to you and answer all your open questions. Thank you very much for your attention and participation in this webinar. Meeting you on our webpage, ametek-land.com. Goodbye.
Manfred, thank you so much for that great presentation, and thank you for choosing a few of our attendees' questions and answering them. We do have some more questions coming in from our attendees, but we are going to answer all of the rest of our questions following today's webinar. Thank you to all of our audience members for being part of this webinar event. Take care, and we will speak with you soon.